Hey everybody, this is chapter 19 of Chemical Structure and Reactivity. I'm your host, Palladium, and in addition to me leading these lectures, I of course have my two beloved assistants, Saya and Larry, to provide you guys some supplementary math notes that overall made the load much easier on me and will make understanding the chapter and the math behind this chapter much easier for you. And so far, here we have the shout out list. If you want to be added to it, by all means, you can message me on Discord or you can leave a YouTube comment. I'll gladly add you to it. So let's just dig straight into it. So, for those who don't know what chemical structure and reactivity is, it's basically a British textbook that covers general chemistry. And overall, I really like the book, and so I'm doing lectures on it now. And we're specifically on chapter 19. And this chapter primarily goes over chemical thermodynamics, which is one of my favorite topics. So we'll primarily first go over some fundamentals, such as the first law of thermodynamics and how we can apply it to gas expansions. And after that, we'll cover some additional concepts such as internal energy, enthalpy, and Gibbs free energy. Then, to cap it all off, we'll talk about equilibrium and how the Gibbs free energy is connected to both equilibrium and other concepts in thermodynamics. Now, I will have to say, this chapter is only 40 or so pages, so it's really short. But with all things in this book, in my opinion, this goes really in depth onto chemical thermodynamics, especially in the mathematical derivations. So do expect some fun, even if it's a short chapter. And in addition, while we're talking about chemical thermodynamics, if you guys know Kuravax, he's essentially, if you don't know him, he got 2 times medals in the International Chemistry Olympiad, and he did do a lecture on YouTube about chemical thermodynamics for the Baltic Chemistry Olympiad, so I would suggest checking that out too. He's much better at this chemical thermodynamics stuff than I am, and I would know really well that he'd roast me on this. But anyways, roasting or no roast, let's get straight into this. So, in this book, chapter 19 is not the first time we talked about chemical thermodynamics. We talked about it actually back in chapter 17. And back in chapter 7, back in chapter 7, we talked about the basics of thermodynamics and how we can build some concepts such as entropy from statistical mechanics, which is overall pretty fun. And we talked about state functions, we talked about entropy, enthalpy, and the Gibbs free energy, which are really foundational concepts in thermodynamics. And the authors say that back in chapter 7, the entire aim of covering chemical thermodynamics was to learn it as quickly as possible. So what this chapter hopes to do is it hopes to fill in some of the more fine details that we didn't cover back in chapter 7. And now, since we're in the more advanced section of chemical structure and reactivity, we will be covering some calculus, and we will be using calculus for derivations, which I get it, it's totally fun stuff. Now, if you guys remember the 3 laws of thermodynamics, the first law states that energy cannot be created nor destroyed, and that it's simply transformed from one form to another. Now, one can bring up the idea of nuclear fission. And the way nuclear fission works is, imagine that you have some sort of nucleus, like the uranium nucleus. In that uranium nucleus, if you make it unstable enough, it will eject a few neutrons, and that will lead to a nuclear chain reaction. But how exactly does this make energy? Well, when the nucleus splits, a tiny bit of the mass actually gets turned into energy. And so when I was an inexperienced freshman, I thought, energy is just appearing out of nowhere in this situation, right? So the first law of thermodynamics isn't really true. But keep in mind, that was back when I was a dumb freshman. And so I didn't realize that Einstein's equation, E equals mc squared, stated that mass and energy are basically the same thing. So even if mass gets converted into energy, that energy isn't coming out of nowhere. It's simply just mass converting into energy from E equals mc squared. Now, talking more about energy, it can come in many different forms. I'm sure you've covered it in your basic science or physics classes. But in thermodynamics, we're primarily concerned about heat, which is the transfer of energy from one object to another, work, and internal energy. And just for a short description of heat, heat is the energy that is transferred between two objects due to a temperature difference. Now, what about work? Well, work is a pretty basic concept when your physics teacher usually introduces it. You usually see it as the dot product of the force vector times the displacement vector. And basically, if you apply a force to some sort of object, and that object moves a certain distance, and you actually did mechanical work, then hey, you actually did work on that object. And a more advanced way to think about work is imagine you have a force field. And a force field is basically a vector field telling us, hey, if I stand at this point, I will have this particular force applied onto me. By taking the path integral of the force field, as long as the path integral is not zero, you did mechanical work. And therefore, if we have 2 points, a starting point and an end point, the amount of work that we do is very much dependent on the path that we take. Now, this is for a very special case where we use non-conservative force fields. There are certain force fields out there called conservative force fields, where if you have an endpoint and a start point, no matter the path you take, the work will be the same. And in a conservative force field, we can define something known as the potential energy, which is a state function. Now, what a state function is that it's basically a value that only depends on where you start and where you end. Mechanical work is an example of a path function, but potential energy is a state function. But that's enough about force fields, path integrals, and all that. Let's talk about work and how that relates to thermodynamics. So in this chapter, we'll primarily be looking at the work done by a gas when it expands. And also, another type of work that we'll go into is electrical work, which is when a charge moves in an electric potential. And this will be particularly useful in electrochemistry. So we've talked about heat and we've talked about work, but we also have to introduce a third quantity known as internal energy. And it's different from heat and work. And that's in the fact that it's a property that an object just has. And the way we can imagine it is that it's energy that's stored inside an object, which can turn into another form. And in fact, internal energy, very similarly to potential energy, is a perfect example of a state function. Now, the way to write it that you usually see in your chemistry class is that delta U, the change in the internal energy, is equal to the heat plus the work done. Now, you can also write this in differential form, which is a form that relates to calculus. And what this differential form states is d. D means a tiny change in something. So a tiny change in the internal energy is equal to a tiny change in the heat plus a tiny change in work. I accidentally forgot to hit shift on that equal sign, so it unfortunately isn't a plus, but you get the point. Now, if you have a gas in the system, the molecules, let's say for example you have a gas in a container, the molecules are going to be bouncing around they're going to be applying some sort of pressure on the walls of that container. And so the work done on the gas is the negative of the work done by the gas. And that's simply just a perspective that we get from looking at the system two different ways. And in fact, we can calculate the work done by a gas expanding. And so imagine we have a gas confined in a piston, and the internal pressure from the gas is Pint. Well, the work that's done by the gas over a small distance dx is the external pressure times the area of the piston times the small amount dx. Now, in a three-dimensional world, we can also define this by the external pressure times a tiny change in the volume. And the total work done is the integral of that Pext times dV over the total volume. And this is an example of a reversible process. And when I mean reversible, I mean if we introduce a tiny infinitesimal change in the pressures, then the system can go from one state to another. And so this work done by a gas expanding is an example of a reversible process. And right here, you can perfectly see the amount of pressure and volume and the pressure volume graph. Now, what if I told you that we can link the idea of the work done by a gas with the ideal gas law? So the ideal gas law is a really simple law stating that if you have a gas, the pressure times the volume that the gas occupies is equal to the moles of gas times the gas constant times the temperature. PV equals nRT. And we can derive for P. And the internal pressure is going to be equal to nRT over V. And using this definition of internal energy, we can change the integral that defines the total work done by or on the gas, used by substituting for the pressure. And the exact derivation is in my notes. Now, on another note, we talked about this back in chapter 7 for the second law of thermodynamics. If you have a process that has reversible heat transfer, then the entropy change is defined as the change in entropy is equal to Q rev over T. And what we can do with that is, if we're going to calculate the entropy change for an expanding gas, we can define the reversible heat done on the gas as this. And so we can get the overall entropy change, which is pretty cool stuff. Now, we didn't talk much about the environment. And so in this part, we'll mainly talk about processes that happen under isochoric, meaning constant volume, and isobaric, which are constant pressure conditions. And these scenarios will allow us to introduce enthalpy, which is equivalent to the total heat transfer or heat flow in an isobaric environment. So to start, if we hold a system at a constant volume, it cannot expand nor contract, meaning that no work can be performed. Therefore, the total change in the internal energy is just the heat flow, which is really simple. And in fact, this is the exact principle behind bomb calorimetry. And the way that the calorimeters work is you have some sort of substance and you make it go through some sort of reaction, like combustion. Since we know that the total change in the internal energy is Q in this ideal calorimeter, all we have to do is measure the heat transfer. And in fact, in calorimetry, we talk a lot about heat capacities. And for a quick definition, The heat capacity is defined as the amount of energy that's needed to raise the temperature of an amount of material by some amount, which is usually 1 Kelvin or 1 degree Celsius. And so this is an extensive property, because imagine if I have 1 gram of iron versus 10 kilograms of iron. If I applied the same amount of energy, then of course the 1 gram of iron is going to heat up a lot more than the 1 kilogram, meaning that this is an extensive property. However, something like the molar heat capacity is an intensive property, meaning that even if I have 10 kilograms or a billion kilograms of iron, the molar heat capacity is going to stay the same because it's the amount of energy needed to raise a specific amount of material, 1 mole of material, by a certain amount. Now, using heat capacities, we can actually derive the heat capacity as the derivative of the molar internal energy with respect to temperature. And going on from isochoric conditions, let's talk about isobaric conditions. So under constant pressure, in isobaric conditions, we can replace the work term in the internal energy by the negative of the external pressure times the change in volume. And from this, we can actually define a quantity known as the enthalpy, which is defined as the internal energy plus P times change in volume. And we can write this in differential form. Now, in an isobaric process, an infinitesimal amount or an infinitesimal change in the enthalpy is going to be equal to an infinitesimal change in heat, which is, again, a key principle in calorimetry. And so, using some more math, we can figure out these heat capacities as functions of the enthalpy. And in fact, this can be utilized in other theories, such as the kinetic molecular theory of gases, to define the total internal energy of a gas system. Next, let's talk about the Gibbs free energy. So back in chapter 7, we stated that the Gibbs free energy is equal to the enthalpy minus the temperature times the entropy. And in differential form, we can derive this using a whole lot of terms. And one particular rule that we use when deriving this is going to be the product rule, which is when you take the product of two different functions with respect to a variable, which we usually cover in Calculus 1. But anyways, going back to the differential form of defining the Gibbs free energy, we can divide everything by T to yield different expressions for the Gibbs free energy. And by using this differential form, we can integrate, and by making a few assumptions, we can simplify it as a function of pressure. And this is especially going to be relevant when we're looking at scenarios where a gas either gets work done or the external surroundings do work on the gas system. Now, gases have different pressures, don't get me wrong. But imagine you're trying to study Gibbs free energy uh, from, and you have two different gases, nitrogen gas and air. Nitrogen gas is, of course, a pure gas, and air is a mixture of gases. But how are we supposed to calculate the Gibbs free energy for a mixture of gases is not pure? Well, we can simply utilize Dalton's law of partial pressures, which states that the total pressure of the gas is the sum of every single partial pressure. And extending that to the Gibbs free energy, we can calculate the Gibbs free energy for these separate gases using their partial pressures. And we can sum that all up to find the Gibbs free energy of the norm of the gas mixture. And in fact, when we have gas mixtures, the process of going from separated gases to mixed gases must be accompanied by an increase in the total entropy of the universe, or in other words, a negative change in Gibbs free energy. Now, in fact, the concept that I discussed before about using Dahl's law of partial pressure is actually found here, where we use mole fractions and we sum all of the Gibbs free energy together. Now, going on to chemical equilibrium, this is one of my least favorite topics, but back in chapter 7, we learned that the standard change in Gibbs free energy is linked to the equilibrium constant. In other words, the change in standard Gibbs free energy is equal to negative of the gas constant times the temperature times the natural log of K. And when K is equal to 1, meaning that the system is in perfect equilibrium, then the change has to be 0. And we can use the graphs here in figure 19.13 to find the minimum, or we can find the change in standard Gibbs free energy. And we can use more math to determine the heat capacity as a function of temperature. And in fact, you can see that we use the same thing, Dalton's law of partial pressures, to figure out the Gibbs free energy. Now, going on to heat capacity, for many materials at low temperature, the heat capacity obeys something known as Debye's law, which states that at low temperatures, it's proportional to the cube of the temperature. So, to summarize this entire chapter, there are many different points in thermodynamics that come back to the first law. Gas expanding and contracting in a container is a good way to understand the concepts behind thermodynamics and the math. Heat capacity can fully depend on the temperature, and the Gibbs free energy is crucial and involves a lot of calculus. Now, as for a sneak peek for you guys, since I love my audience, the next chapter is going to be my favorite in the entire book. And when I say favorite, I mean my absolute favorite, which is going to be chemical kinetics. And although this is intertwined with the concept of equilibrium, we will go over a lot of the exciting conceptual stuff in chemical kinetics, such as concentration, integrated rate laws, and along with some other theories such as collision theory and transition state theory, which I personally do work on and I consider absolutely fun.